At first, 3I, Atlas, looked like a familiar kind of cosmic traveler. A comet, a dirty snowball thrown into the darkness between stars. Except this comet did not come from our solar system. It came from somewhere else. And when astronomers finally had a chance to examine what was inside it, they found a chemical fingerprint that looked profoundly unfamiliar. The James Webb Space Telescope detected gases and isotopes unlike those normally seen in our own comets, including an extraordinary abundance of carbon dioxide and an unexpectedly rich supply of methane. So what exactly is 3I Atlas? The answer begins on the 1st of July, 2025, when a NASA-funded Atlas survey telescope in Chile reported an object that was moving far too fast and along the wrong kind of path to be a permanent member of our solar system. Astronomers traced its trajectory backward and discovered something remarkable. This object was not orbiting the Sun in the usual sense. It was passing through. That distinction matters. Our solar system contains countless comets and asteroids, but they were formed here. Inside the disk of gas and dust that surrounded the young Sunday 3I, Atlas was different. Its trajectory showed that it had arrived from interstellar space, making it only the third confirmed interstellar object ever identified passing through our solar system. The first two were Oumuamua in 2017 and Comet 2I Borisov in 2019. Now, there was a third visitor, and this one gave astronomers something the first two could not provide as clearly. A comet with an observable coma. The glowing cloud of gas and dust released when sunlight warms an icy nucleus. That made 3I, Atlas, an unusually valuable target. Because astronomers could not travel to it, they had to read its chemistry from light. This is where spectroscopy becomes powerful. Spectroscopy is essentially the process of splitting light into its component wavelengths and looking for fingerprints left by particular molecules. NASA's James Webb Space Telescope was built for exactly this kind of work. Using Webb's near-infrared spectrograph, known as NIRSPEC, researchers examined the gases surrounding 3I, Atlas, and found something striking. Carbon dioxide dominated the coma far more strongly than it normally does in comets from our own solar system. The reported carbon dioxide to water mixing ratio was about 8-to-1. That is an enormous difference. Water is normally one of the central ingredients astronomers expect to see when studying an active comet. But in 3I, Atlas, carbon dioxide was unusually prominent. Why would a comet from another planetary system be so rich in carbon dioxide? Researchers led by Martin Cordiner and colleagues proposed several natural possibilities. The object could have formed in a region of its original planetary system, where carbon dioxide ice was especially abundant. It may also have experienced a different radiation environment, or its internal structure could have suppressed the release of water compared with other gases. None of these explanations requires anything exotic. But then Webb found another clue: methane. In later mid-infrared observations with Webb's MIRI instrument, astronomers directly detected methane in an interstellar object for the first time. Methane is a simple molecule made from carbon and hydrogen, but its location inside 3I, Atlas, was important. The methane did not behave exactly like the water. Its production became noticeable after the comet had already passed the Sun, suggesting that some of the methane may have been buried beneath the object's outer layers. Heat from the Sun could then have penetrated deeper into the nucleus and released material that had remained protected for an extremely long time. Think of it as opening a frozen time capsule. Except this time capsule was not made in our neighborhood. It may have formed around another star billions of years ago. And that possibility became even more interesting when researchers examined isotopes. An isotope is simply a version of an element with a different number of neutrons. The chemical element is still the same, but the extra mass preserves information about the environment in which the material formed. One of the most important isotopes here is deuterium, a heavier form of hydrogen. Webb observations found unusually high deuterium to hydrogen ratios in the water associated with 3I Atlas. Researchers also found unusual carbon isotope ratios. These numbers are not just chemical trivia. They can act like fingerprints of ancient environments. And there is another reason the chemistry matters. Astronomers are not simply cataloging what molecules exist. They are comparing their relative amounts, their isotopic patterns, and the places where those molecules appear around the nucleus. That combination can reveal whether the surface has been altered by radiation, whether different ices formed at different depths, and how the object may have evolved before it was ever ejected into interstellar space. In other words, the strange chemistry is not one isolated anomaly. It is a collection of clues that point toward a history we can only reconstruct indirectly. The measurements reported by researchers, including Martin Cordner, Nathan Roth, Stephanie Milam, and their collaborators, suggest that 3I, Atlas formed under conditions very different from those that produce the comets we know from our own solar system. Some modeling goes even further. The isotope measurements have been interpreted as evidence that the object formed at extremely cold temperatures, potentially below about 30 Kelvin. That is roughly 30 degrees above absolute zero. Under those conditions, molecules that would normally remain gaseous can freeze onto dust grains and become incorporated into developing planetary bodies. And this leads to one of the strangest possibilities surrounding 3I, Atlas. It may be ancient, very ancient. One analysis of its carbon isotope composition suggested that the object could have formed roughly 10 to 12 billion years ago, when the Milky Way was much younger than it is today. If that interpretation survives further testing, 3I, Atlas would not simply be a visitor from another planetary system. It could be a preserved fragment from an era of the galaxy that existed long before Earth. Imagine what that means. Earth is about 4.5 billion years old. The Sun is roughly the same age, but a comet, carrying chemical evidence from a planetary system that formed many billions of years earlier, could preserve a record of conditions that existed before our own solar system was born. And suddenly, the object is no longer just a strange comet. It becomes a messenger from another chapter of galactic history. But there is an important distinction here. NASA's observations support the conclusion that 3I, Atlas, is an interstellar comet with unusual chemistry and an ancient-looking isotopic signature. They do not show evidence that it is an artificial spacecraft or evidence of extraterrestrial technology. Suggestions that the object could be artificial remain speculative and are not part of the scientific consensus. That distinction matters because 3I, Atlas, has attracted extraordinary speculation. Some researchers and commentators, including Avi Loeb, have publicly discussed whether unusual properties of interstellar objects deserve consideration beyond ordinary cometary explanations. But speculation is not evidence. The strongest evidence we have points toward a natural object. A very unusual natural object, perhaps. But still a comet. Its strange chemistry may actually be more scientifically valuable than an artificial explanation would be. If 3I, Atlas, formed under conditions unlike anything represented in our own collection of comets, then astronomers are being given a direct sample of how planetary systems can differ from one another, and that is something scientists have never been able to study this closely before. The first interstellar object, Oumuamua, gave astronomers a glimpse of material from another star system, but it was difficult to observe in detail. Borisov looked much more comet-like, but it still offered only a limited chemical window. 3I Atlas is different. Astronomers have been able to observe its gas production, its dust, its isotopic composition, and its response to sunlight with a growing fleet of instruments. NASA's Hubble Space Telescope observed it. Webb observed it in infrared wavelengths. NASA's SphereX mission tracked its brightening and detected organic molecules in its coma. Other observatories around the world added measurements that helped scientists reconstruct its path and physical behavior. Each observation adds another piece to the puzzle, and some of those pieces are surprisingly old. The chemistry suggests a birthplace unlike our own. The isotopes suggest an unusually cold formation environment. The trajectory tells us it came from beyond the solar system. And the object's speed ensured that it would not stay. That last fact makes the investigation urgent. 3. Atlas is not going to circle the sun forever. It entered our solar system, passed through the region around the sun, and continued back toward interstellar space. Eventually, it will become too faint for even our most powerful telescopes. Then it will disappear. No spacecraft will catch up with it. No laboratory will receive a sample. Astronomers will have to rely on the photons and particles that reached their instruments while the visitor was close enough to study. That may be the most remarkable part of the entire story. Humanity has learned something about another planetary system without ever seeing that system directly. A small piece of it crossed our path, and for a brief moment, our telescopes were pointed in exactly the right direction. The mystery is not whether 3I Atlas is an alien spacecraft. The evidence does not establish that. The deeper mystery is arguably more profound. How many different kinds of planetary systems have existed across the history of the Milky Way? How many icy worlds formed under conditions completely unlike those around our sun? And how many ancient fragments are drifting through interstellar darkness right now, waiting for a civilization to notice them? For most of human history, those questions were impossible to test. Now, they are becoming observational science. 3I. ATLAS has shown that material from another planetary system can enter our own and leave behind measurable chemical clues. Its carbon dioxide, methane, water, and unusual isotopes are telling astronomers that the recipe for making icy worlds is not universal. There may be countless recipes. Some may produce comets that look familiar. Others may produce objects that seem almost alien, even though they formed through completely natural processes. And that is why 3I, ATLAS, matters. Not because it has been proven to be artificial. It has not. Not because scientists have solved every mystery surrounding it. They have not. It matters because for the third time, nature has delivered a piece of another planetary system directly into our cosmic neighborhood. And this time, humanity had the instruments to read it. The comet that first appeared to be just another frozen traveler was never just another comet. It was a fragment of somewhere else. Perhaps somewhere unimaginably old. Perhaps somewhere chemically unlike the world that made us. And when 3I ATLAS finally disappears into the darkness between stars, it will take most of its secrets with it. What remains will be light, spectra, isotope ratios, and a handful of observations recorded by machines on a small planet. For a civilization that has only just learned how to look beyond its own solar system, that is an extraordinary amount of information. But it is also a reminder, the universe is not running out of mysteries. Humanity is only beginning to learn how to read them.